So from here to here, right? Yeah. So when you follow the bond, so I'm taking these electrons and I'm pushing them down here. Okay? So that generates a new bond between this carbon and this oxygen. And of course I need to displace, so this is a substitution reaction of oxygen essentially. So I need to kick out the OH so that I don't violate the octet rule on the oxygens. And of course I haven't touched the oxygen boron bond. That's just there. So when you look at the product, I have the carbon here, and this is my oxygen. And since I took the electrons in the carbon-borane bond, there's no bond over here anymore. But there's still this bond because I didn't touch them. So it's essentially a shift. It's like the carbocation shift, where we transfer a hydride or a methyl group onto the next carbon. So essentially I take the electrons and I move the group over into one atom over.
And what's pushing that?
The driving force is more of a pull because we break the oxygen-oxygen bond. So essentially that is a good leading group because you want to break that very reactive bond. And so it's more a pull than a push. Yeah?
Is there going to be any configuration? Is that going to be formed at all?
Very small amounts, yes. So usually 2% or 3% that you actually see from the carbon production. And the major reason is that the borane is very electron deficient. And so when you look at the mechanism, I drew both electron movements at the same time. But imagine that the electrons first flow to the boron. Then you get a carbocation, and that will be the tertiary carbocation. So the reason it really is the same, you form the more stable carbocation before the hydride is being transferred. It's immediately quenched, and it's, since the boron ends up where the hydrogen sits, the product looks like it is an anti-Markovnikov product, but the mechanism still follows the carbocation stability. It's just a very fast reaction. So, like in any case, then, since you have roughly carbocation selectivity, you do get a little bit of the other product depending on the relative stability. So you get 2 or 3%, but it really depends on the substrate. But for all needs, you can assume that this mechanism, gives you a single product. But in the back of your mind, you should know in organic chemistry, they always find other products in there because there are other pathways that are feasible. That's true for this as well. And mechanistically, this is very similar to the Markovnikov hydration or the oxymercuration reaction because we're also partially involving transient carbocation intermediates, but they're very transient. Another aspect, of course, is the size of the boron. The bigger the boron, the more it wants to move away from the more bulky carbon. And so you get better selectivity with larger borane reagents. Okay? And I'll get to that right away here, discussing actually the nature of the borane here that I'm using. Okay, any other questions for just the conversion here and the mechanism of the hydroboration? Okay, let's look at a little bit of reagents. So I mentioned very briefly that borane doesn't really exist. Well, what does exist is a reagent that is diborane. So that's an actual reagent. But diborane is a gas. It has interesting 3-atom 4-electron bonding. So it has an unusual bonding. But that's more for the inorganic chemist. So I'm just putting this in parentheses here. You can read up on that, and there, of course, if you go into borane chemistry, you can talk about the special bonding situation in borane. But I'll keep that out here. But diborane is a reagent that can be used. It's very aggressive, toxic, difficult to use. So generally, people don't use diborane. What is much more common, what is popular, are complexes of borane. And one complex is the THF complex. So this is borane THF. complex. Okay, and you can see why that is forming, because the borane again coordinates, of course, to one of the lone pairs. And so it kind of makes a complex with the Lewis space to get back a little bit of the electron octet that it would like to have. Another popular complex is the dimethyl sulfide complex. Borane dimethyl sulfide complex. Okay. I'm just drawing it like this. So this is borane dimethyl sulfide complex. And so this is another popular reagent. So in many cases, you might write BH3, but what you're really referring to is either the THF complex or the dimethyl sulfide complex. And those are liquids, and they're usually used in solution in THF or another solvent, and they're much easier to handle. So those are the popular ways to actually use the borane reagent. And not so much BH3 doesn't exist, diborane exists, but it's very difficult to handle because it's a reactive gas. Okay, let's look at just regioselectivity. That goes back to the question, do we get isomers? And it depends on the system. So one particularly bad system, so let's start with this one first, a good one. Yeah, so this alkene gives a very high selectivity. And so through the hydroboration, then hydrogen peroxide, sodium hydroxide reaction, so hydroboration, oxidative workup, you usually get a very, very high selectivity of the anti-Markovnikov product, which is this system. And so we get here greater than 98% of this selective alcohol formation, and that's the anti-Markovnikov product. So less than 2% of the corresponding regioisomer. So regioselectivity on these cases is generally very high. But there are exceptions for regioselectivity where it starts to drop. And that's when the differences in sterics and electronics become, of course, much more subtle. So a compound that has low selectivity is this compound, and here the difference, of course, is only sterics. This is larger than this. There's a small sterics difference. And in fact, when we do a hydroboration oxidation, I'm using the quotation marks just for the standard conditions here, I get pretty much a mixture, almost a 1-to-1 mixture. So I get this predominantly, but I also get the regioisomer. Just this. And the ratio is 57 to 43. So almost 1-to-1. So here we get a mixture of alcohols, and that's not so good. So what we can do now is use a bulkier hydroboration agent. And a very nice one here is 9 ppm. That is 9-boron bicycle non-A. Sounds a lot more complicated than what it is. But again, it will test your abilities to draw 6-membered rings. So I hope you've been keeping up the exercise. What did we say? Like 50 cyclohexanes every morning, 50 to 100, right? So I hope everybody's done these exercises. If not, it's never too late to start them up again. Okay, so this is 9 ppm. Has only one hydrogen and much larger groups now in the borane. And so here the selectivity for this system now, the same conversion here is very nice. So we get 99.8 to 0.2%. So this is this same reaction with 9 BBN, 9 boron bicycle non-N. So the same conversion, these two alcohols up here. This is now favored almost quantitatively, 99.8%, only 0%, 0.2% of the radioisomeric alcohol. So again, by changing the substituents on the boron, in this case making them much more bulky than just hydrogen, we can shift the equilibrium in favor of what is the sterically less with boron addition product and ultimately the sterically less with alcohol after the oxidation with basic hydrogen peroxide. Okay, that's it for today, and we'll have one more class, and that is on Thursday, and we'll cover